and it's fairly interactive. So we're moving on from the wave model of light to the ray model of light. And so we see this familiar image of these concentric circles, right? And as time goes on, those waves, they travel outward. And so this talks about how we draw those rays in the direction that the waves are traveling. So this light here emits rays from it in all directions. All objects that we see have light that's being hit on them, and they reflect light in all directions. That light reaches our eyes, and that is what allows us to see it. And so this first part, let's see. Get this top off here. We're going to be looking at a pinhole. So what we're going to have is this light source here, and we're going to have this pinhole that light is going to be shining through. So I'm going to go ahead and turn this off for a second. And first, we're going to take a look at what happens with this as we shine light through this pinhole. So let's see. I think because that's still on, I don't want to turn it off all the way though. Do you guys see that the pinhole of light there? Mm-hmm. As I move this to the left, where does the pinhole of light go? And as I move this to the right, where does the pinhole of light go? It's hard to see. I'll pull up the videos then. All right, so again, that situation, pinhole in a piece of paper. Can you see that spot of light up there? He's going to take this and move the flashlight to the right and watch where the pinhole light moves to the left. When we move to the left, the pinhole moves to the right. And then if we move up and down, oh man, we can watch where this moves. Sorry for the technical difficulties here. I think it's because I'm trying to run too many things at once with this recorder. So we can use the ray model of light to describe where this light is moving to and from. So what we can do is say light is moving from this source in all different directions, right? Some of it moves out here and hits the screen and doesn't make it through. But what about the light that moves towards this hole, right? It'll continue through and hit the screen. We're going to use a straight edge for this activity, so you're probably going to want to grab one. There might be some left out. Oh yeah, there's 3 right there. So then here, this is the side view of what's happening. So this would be looking at the light shining towards the screen like this, and we see the pinhole and it travels through the pinhole and hits the screen. And then this is the front view looking at what we saw in the video. There'll be a little, spot here. Right? So what would happen if we had 2 mag lights? 2 of these flashlights and a single pinhole. What do you guys think will happen?
So like there's two, but the light from both goes through the same hole.
So what's shown here, there's two mag lights, one hole. So we're going to get two bright spots on the screen?
Yeah.
And what if we covered up the top light? Which hole would disappear? So the bottom, because this light from the top is going through to the bottom, this light from the bottom is going through to the top. So on the next page, you could go ahead and use your straight edge and show that. So this light here going through to the bottom, this light here going through the hole to the top. Again, we still have rays going at all angles and hitting the screen, but those are being blocked by the screen. So the only important rays are the ones that make it through the hole.
Are they supposed to have like dots at the end?
So I put a dot here because that's where it hits the screen.
Oh.
And it makes it's actually a bright circle. So it's a little bit misleading that we draw it as a dark circle, okay. But that's where those light spots are on the screen. And these movies are available on your website, the Blackboard website right below the lab. This second video shows what happens when we have two mag lights here and a single pinhole. We get two bright spots. In this case, they're side by side. Mag lights side by side, spots are side by side as well. So go ahead and read through the next paragraph. It talks about important rays for us to draw. In this case, we're going to be looking at this blocker without any pinholes in it. And we're going to be considering what happens to the shadow that creates. So here's some important rays are those boundary rays, the ones that hit the side of the blocker. And then any rays outside of that angle are going to be light coming through. The lights that are hitting the blocker are the rays that are hitting the blocker are going to be shadowed out. So what do you think is going to happen when we have our mag light shining on our blocker here and we move the mag light above? What's going to happen to the shadow of the blocker in this case? Move downward. And let's go ahead and try and show that with our way down. So start with those boundary rays, draw a few rays that make it through, and maybe draw a couple of rays that get blocked off. And then from there, we can imagine that if the blocker was center when the mag light was centered with it, when it moves up, this, you guys said, is going to move down. So we can imagine it's now down here. That's what this video shows. The mag light's turned on. You move it side to side, up and down. See if it'll play smoothly for us. The shadow moves opposite of the movement of the mag light. We can also see as the mag light gets closer and further away, after it moves up and down, I think it's going to get closer. Oh, no. So imagine what's going to happen here as this mag light moves closer. What's the shadow going to do?
Expand.
What'd you say?
Like expand.
Expand, yeah. And can we show that with our ray diagram too? So go ahead and do that. Show that as this mag light moves closer, the boundary rays are now going to extend pretty much to the edge of the screen. So any of the rays that make it through are not going to be hitting the screen. And any rays that could hit the screen are going to be blocked out. All right, so read through this next question. We're imagining that we have a mirror, and this mirror has all but this little strip covered up, and we have a light source. So this light source is going to emit a ray towards the mirror. If it wasn't there, it would extend beyond it, right? It would just keep going. But since the mirror is there, where is it going to be reflected to, and who is going to be able to see the light if they put their eyes there? B. And that's using the idea that reflected light reflects at the same angle as the incident light, right? So this incident angle from this incident ray is the same as this reflected angle from this reflected ray. And that's the law of reflection that some of you saw as you worked through the tutorial, right? That this incident angle is going to be equal to the reflected angle. Now, what's important, though, is that we establish this normal line. Once we got into the heat of things with this lab last class period, a lot of students forgot about that normal line, and they just tried to measure the angle between incidence and reflected. So our normal line is always perpendicular to our surface. If our surface is horizontal, our normal line is going to be vertical. If our mirror is vertical, our normal line is going to be horizontal, or at any angle. If we're at this angle, our normal line is going to be like that. So whatever our surface is dictates our normal line. And our angle of incidence is measured from the light source to normal, and our reflected angle is measured from normal to the reflected. So there's many rays coming from this, like say if this was an object emitting light, there would be incident ray and reflected ray, and incident ray and reflected ray. And for each of these, we'd be able to draw a normal line and say this theta incidence is equal to this reflected angle. But again, we sometimes only draw a few rays that help us understand and analyze the situation. So go ahead and take a minute and use that law of reflection to solve this triangle. If you did the tutorial, it'll look familiar. In this case, I'm giving you angles, so you can do it mathematically with numbers, whereas on the tutorial, you'll have to do it in terms of theta. You guys figure out theta 3. Yep. So you say 90 because this normal line is perpendicular to this horizontal line.
Right.
So theta 3 is 90 minus theta 2. And then how are we going to figure out theta 4? Did you figure out theta 4? What did you use?
180 minus alpha minus theta 3.
So you use the principle that all three of these angles add up to equal 180. Because we have a triangle here. All three of those angles, theta 3, theta 4, and alpha, are equal to 180. And so that's where Claire got 180 minus theta 3 minus alpha is equal to our theta 4.
Theta 3 minus alpha equals 4.
No, we have to subtract alpha and theta 3. To get theta 4 is equal to 180 minus alpha minus theta 3 minus 30 minus 65 was theta 3 was 65, right?
Yeah.
And then from there, how are we going to figure out theta 5?
Isn't it 90 minus theta 4?
Because this is a normal line. This light reflects, and so it's perpendicular here. This is 90 minus theta 4 will give us theta 5. Cool. And then theta 6 is equal to theta 5, thanks to our law of reflection. All right. I talked with some of you about the Blackboard Mastering Physics problem. I'll go ahead and let you guys know for the tutorials in chapter 18, I went ahead and made it so you had unlimited attempts and didn't get point deductions because of those vector problems. So you'll have as many attempts as you want and you won't get points deducted. There's more ray diagrams in chapter 18, part 2. But let's go ahead and open that one ray diagram up. And I'll show you how you can hopefully get through that. Okay, let me restart this. So this is one where Vittorio wants to see the logo on his shirt. So this incident ray here is going to reflect off the mirror and come back into his eyes. So I'm going to extend this. It's about 1 right now, so maybe I'm going to make it 4. And then I'm going to decrease the angle. This angle here, our normal angles, our angles normally are measured from horizontal, right? Whereas in this, we're talking about normal angles, but this angle here is measured from horizontal. 173, and then I'm gonna try this one out. So it goes about there. 173 is 7 degrees is its corresponding angle above horizontal. 173 is 7 degrees above horizontal in the other direction. And then I'm gonna make that a little bit longer. So that looks about right. We're gonna see if it'll take it.
I know.
So that's how I go about doing it, increasing the length, and then we want those two angles to be the same. All right. Now, these images here are collected from week 6. I have these videos that I showed you guys you can view. Also, this plane mirror reflection simulation is the same one I gave you for your video learning resources. So a lot going on here. I'm going to go ahead and compress it here to this single point and then bring all these together. So when we have our single incidence ray, this is our incident ray here, right? Our mirror is vertical. Our reflected ray is here. And what's this yellow dashed line? Normal. And this angle here is going to be the same angle. Okay, now it shows up. That's here. And this ray that extends from the reflected ray back to where this image appears, somewhere back over here. Somewhere here is our image behind the mirror. This angle is going to also be the same angle. So that's why on your handout, I say theta I is equal to theta R, which is also equal to that theta. In last class period, we actually started calling this theta V, because we call this the virtual image, and this is the virtual angle. Whereas this is theta R, our reflected angle, and this is theta I, our incident angle. So you're going to want to be able to identify an object has an incident ray and a reflected ray, and drawing this reflected ray straight back leads to your image. But we don't know exactly where the image is based off of that single ray analysis, right? I can't say exactly where it is along here. So what I'm going to do is add a second ray. And we can see that our incident location, the location where these two virtual rays intersect, will tell us the exact location of our image. So this is why we need at least 2 different lines to measure 2 of these ray analysis. And again here, this is going to be a different theta I. This is going to be different theta I and a different theta R and a different theta V. All of these 3 are going to be equal though. And based off of those 2 rays, we can get the location of that. However, for in your lab, I'm going to ask you guys to, I'm just going to delete this. I'm going to ask you to use 3 different lines because we know that 2 lines are going to cross at some point, but if you could get that 3rd line to cross using your ray analysis, we'll be certain where that image is located. If it's an extended object, in the post-lab questions, it asks you to find at least 2 rays from the top and 2 rays from the bottom so that you can draw. Here, this is a little bit clearer. You can see from the top, these 2 incident rays and reflected rays draw back to where the tip is, and these 2 incident rays from the tail and reflected rays draw back to where the tail is. So those are going to be what you were supposed to do in ray tracing 2 that we skipped, and then questions 2 through the end deal with this extended object reflection, and that's going to be, those last questions are going to be worth extra credit since we didn't finish it in lab today. So let's go ahead and hop to it here. We'll walk you through these first few. So we're going to start with this first image location. So I'm going to put on my dock cam and get some clean sheets of paper. You're going to want to grab one of the cardboards, a mirror, several pins. You'll only need 3 or 4 pins to start with, and then we're going to need more after that. So for our clean sheets of paper, there's scratch paper up here. You can come and grab. If you can find one-sided scratch paper, that's good. If you want to grab clean sheets, there's also clean sheets. Okay. All right, so following these directions, I'm gonna first, this is the mirror I'd recommend using. Not the best mirror, but you can see through the reflected surface. And what's nice is you could see through the back of it. So first thing is to draw where your mirror surface is located. That way, in case you bump your mirror and for analysis later, we know where it's at. So we have that line there for our mirror location. And then I'm going to place this object in front, and I'm going to call this the object. And that object is going to have an image in the mirror. So go ahead and look in your mirror and see that a certain distance behind it in the mirror, if you look in the mirror, can you see your image of the object? You need to actually look like I'm looking at it. So look in your mirror and see the image. So from this front view, look into your mirror. And do you see that reflection? And put a pin exactly where that reflection is. Now for this first part, it's pretty simple. You can just remove it. And what I ask you to do is to measure object to image. What's the distance from the object to the mirror? Me, I got about 6.8 centimeters. Is this distance from the object to the mirror? Distance of the image to the mirror was about 6. Did I do that badly? Yeah, apparently I did. Hopefully you got a little bit better than me. Because what would you expect the distance behind the mirror, the image appears to be behind the mirror?
Same.
The same. Yep. Okay, and for this next portion, I'm going to put the mirror back. It says grab a clean sheet of paper. Yeah, so I'm going to go ahead and restart on a new one just to not get these confused. So you measure those distances and answer there. I also ask you on here to draw these. So draw these on a small scale as you go through them. All right, so here's my new sheet. I'm going to place my object here in front. I'm going to do the same thing back here by placing a pin at the image location. However, what I'm going to do is, it says move your head. Oh, wait, no, I did this wrong. I'm supposed to do my object off to the side of the mirror. I forgot. My object is supposed to be located somewhere over here, right? So that when I look straight into the mirror, I don't see it. So object's off to the side of the mirror so that when I look straight in, I don't see it. So in order to see it, I'm going to have to move my head over here to the side, right? And when I move my head to the side, I can see its reflection right about there. And then I'm also going to place a pin right at the base of the mirror where I see that image in the back. So that is showing where the object has an incidence ray here coming from the object and hitting the mirror at that pin location.
Wait, what is that?
Yeah, how did you find that?
So I basically just looked at where the image appeared behind the mirror, and I placed a pin. I drew a direct line down to the mirror from that towards my eye. So eventually, what you could also do is just place a pin in line with that image location here. Try and do that. Place a pin in line with that image location so that this pin is in line with your image. Does everybody have that? And then you could draw a line directly from your image to that line. Did that work out for you? So look, this is your object and that's your image. So look over here. Do you see the image location?
I see the
And place a pin directly in line with that. So that from your eye to the image, yep. And then that's going to be, yep.
I don't think I got the right location.
Huh?
I don't think I did the right location. I was supposed to put it on this.
Where is your object?
This is.
So we make the line go, which then just there.
Your object.
And then-
Which is the image.
That's the object is.
Okay.
Like between these two.
Mm-hmm.
Yeah, that's gonna be your reflected.
And then you say this one is really?
So wherever your head is, so place your head somewhere. And do you see the image back there? Place the pin so that the pin lines up with the image location. Mm-hmm. Yep. And then draw a line. So it actually doesn't matter where this is just saying this is the location where I placed my eye and saw the image back here. So this is just saying I put my eye here and the image was back there. Which is our incidence ray?
From the object to your mirror.
From the object to the mirror is the incidence ray. And then which is my reflected ray?
From the mirror extending outward towards your eye.
From the mirror to my eye. So this is my reflected. I can also, just to aid myself, I can draw a little arrow there. And so which is my virtual ray then? We call this a virtual image because it's not real. Real image is where we could put a screen and capture an image. This is a virtual image because it appears like light comes from it. And this is the virtual ray. So it appears as if light comes from that virtual image and travels to us. And as that light appears to come from that, it actually becomes the reflected ray. Light actually reflects from incidence and becomes reflected, but it appears as if it comes from that point.
So is the direction of the virtual ray the same as the
Yeah.
reflected?
Yeah, it appears as if it's coming from that image location. Yeah. And so I can go ahead and rotate this for you guys. How do we get our incidence angle? We have to draw our normal line, perpendicular to the surface. We draw a line, right, extending beyond the mirror on both sides. And which is our incidence angle?
From the object
So from the object
to the normal line.
to the normal line is our theta I. Our theta R is the reflected between reflected ray and our normal. And then our virtual ray is between our normal and where it appears to be coming from the image, that virtual ray. So this is theta R. And all of these should be equal. Do you guys want to go ahead and take a moment to measure those? Like, not really, but I'll do it. Yeah, some of those protractors. So to do this, I would recommend placing, this cross. You want to place this cross directly where it hits the mirror. And then you're going to want to look, because 0, it looks like 0 for this one starts up here. So I can measure, this one's about 42 degrees. And then this one, it goes from 180. No, so I'm going to rotate this one and start my 0 here and measure from 0 up to 40. Yeah, 42. Theta R is equal to 42. And then here, I'm going to start with 0 on my my virtual ray and go up here to 42 or 43. And then I can help you with these protractors because they're not the best. But one more thing that we can measure here is I'm going to extend this plane of the mirror, and I can measure my distance of the object here from the mirror and the distance of my image to the mirror. I can measure these two distances, and this distance should equal that distance, like we've seen on the last problem. I think that's the last thing that I ask you to measure on this page.
So we have to draw all on this lab sheet then.
Mm-hmm. Yeah, I asked you to draw a little figure here describing what you have. And then on the next page, you're going to draw the full thing to scale, or roughly. So for the next page, you're going to need a lot more pins. We're not only going to be doing one line of sight like you did with this one, but you're going to want to do 3 lines of sight. So instead of just putting my head right here, I'm going to put my head somewhere else. Let me get this lined up again. There we go. I'm going to put my head somewhere else and put 2 pins directly in line with that reflected pin. And that's going to be a second line of sight here. And then I could even move my head over to this side. Well, I can't really do that over here, and put in 2 more pins. So that's what the next part asks you to do when it says line up 2 pins directly in line of sight, is each of these lines then are going to create a reflected ray, an incident ray, and a virtual ray. A reflected ray, an incident ray, and a virtual ray. And each of those is going to have its own normal line. So just to give you a little heads up on the next part, this is the part where I let the last lab have at it. So go ahead and finish up with the questions on this page. Give me a holler when you have troubles, and I can talk you through the next process, the next step, ray tracing 1, if you have questions on it. And it looks like you guys probably will have some extra time so you could get started on those post-lab questions for extra credit. Any general questions before I let you loose?
Is this the same lab we're going to be doing on Wednesday?
No, on Wednesday we're going to be doing refraction. So today is reflection, Wednesday is refraction. And most likely, I told the other class, like, I'm thinking being able to identify on a figure, if I show you the object and where the image is, to be able to say where the reflected ray is, or where the incidence ray is, or the incidence angle, be able to identify those things, and to do math with those angles, considering all the angles should be equal, just like you saw on the pre-lab to this.